Hi, I'm Jackie Bondell, and I'm here to share with you some work my groups have been doing about contemporary topics and innovative classrooms, gravitational waves and dark matter, leveraging astrophysics research collaboratives to expand physics education content. I would first like to acknowledge the traditional owners of the land on which I'm coming to today, the Wurundjeri people, and I acknowledge and respect the traditional owners of the lands across Australia, the elders past, present, and emerging. So I work with what are two centers of excellence. So they're supported by the Australian Research Council. They are multi-university collaboratives around a common theme, and part of their funding supports collaborative research, diversity in their researchers and their areas of research, as well as outreach. So I coordinate the education and public outreach programs for both the Center of Excellence for Dark Matter Particle Physics and the Center of Excellence for Gravitational Wave Discovery. So my role is to take the research that's being done, find ways to make it accessible and relevant to various audiences, and design and deliver those programs. But I don't do it alone. I want to introduce some people that I've worked with. So Ian Dewey is a physics teacher who has been actively involved with the gravitational waves program we'll speak about today. And in the live session, he will be available to discuss and answer questions, as well as Carlos Lopez, who is the teacher who helped me initiate the Regional Partner Schools program. I also want to acknowledge Maddie Parks, Kendall Jenner, Zach Holmes, Dr. Dan Brown, and Assistant Professor Paul Lasky, who have all worked diligently to help develop the gravitational waves program that I'm going to be talking about today. So we've got two programs that I'm going to highlight. The OSGrav Inspired Project is a hands-on depth study of black hole mergers, and the Dark Matter Inspired Project is a regional schools partnership. So I'll start with the regional schools partnership, and the idea is to find relevance, even some humor in dark matter, and share the search for it with students. And as you may know, dark matter makes up 80% of the mass in our universe, and so the idea is that there's this curiosity about what it is that we don't see in the universe, and that's what we want to try to bring to students. So it ties in with astrophysical observations in the motion of galaxies, its discovery, and that stars and galaxies were moving faster than if there were only light matter, and that led us scientists to term this phrase dark matter. And the reason that we're engaging with trying to focus on bringing dark matter science to regional schools in Australia is because in about 3 hours outside of Melbourne, we are involved in building the Stoll Underground Physics Lab, which is the Southern Hemisphere's first underground dark matter detector. And dark matter in education, it encapsulates the nature of science, those broad scientific contexts like galaxies and gravities and particles. It's connected with work that's being done here in Australia, and it's pretty darn fascinating. So that's why we're really working to try to collaborate with regional schools to try to create some longitudinal programs in which we meet with students and do activities over subsequent years to try to highlight those STEM pathways for students, create opportunities for and resources for regional teachers who very often may not have the accessibility to bring their students to the metro centers for science engagement programs. And I'll make all these slides available after the talk so that you can continue to read through some of the dot points which I may not get to cover in this recorded version. But the idea is we want to build this understanding of big science for society and engagement in places where science is happening locally. And from the perspective of the schools in which we engage, specifically with our pilot school at Stall Secondary, regional schools are pretty limited by geography and resourcing, and but they definitely need to cultivate science in areas such as, energy, renewable energies, agriculture, for the advancement of industry in those areas. So this specifically appealed to Carlos at Stall Secondary School because, it's a relevant long-term engagement with the school. So we have this high impact long-term engagement with our partner schools to create unique experiences for students and teachers, and to create content that can continually be used by teachers. Now, how are we doing this? Well, we're incorporating, arts and innovative design into activities. We're utilizing resources of other groups such as CERN and Perimeter Institute. We're focusing a lot on the nature of science because dark matter doesn't necessarily line up in the curriculum, but we're providing lessons and connecting with local partnerships and assessing our programs in order to try to find the best to see if what we're doing has an impact. So the other program which I will highlight is the OSGRAV Inspired Project, which is a hands-on depth study of black hole mergers. So within the Australian curriculum, physics is constructed around using models, laws, and theories to understand forces, energy, and interactions. And why do we do gravitational waves? Well, the detection of gravitational waves connects with the history and nature of science. It pulls in many astrophysics topics, as well as physics instrumentation and data analysis. So it's very broad in terms of the topics that we can cover. Now, a depth study is just an investigation where a student has to do either by themselves or with others, do some kind of further development of their understanding to go more in depth, hence the name, into one of the concepts inspired in the curriculum. So that's where we focus this program, because we do have a lot of resources that allow students to take a deep dive. Now, our researchers are, they're skilled science communicators and excellent outreach practitioners, in addition to being excellent scientists. And then, we have physics teachers that can be enthusiastic about research. They're cognizant that their students are curious about novel science, and they can be very creative in finding opportunities for their students. And we really want to harness that enthusiasm that some of these physics teachers are showing in their in their goals to try to bring contemporary science to their students. Now, this a little bit more. So the idea is that these things feed each other. So it's sort of like a cycle. The physics teachers are enthusiastic. They work with our researchers. We figure out ways in which we can better communicate, and that loop goes around. Now, there are some challenges. Obviously within the curriculum, there are some topics, especially related to contemporary science, which aren't covered, and not every state has the impetus to try to overhaul that. There's also school level limitations and teacher limitations. There's a lot of inertia, and sometimes places just don't want to rock the status quo. And hopefully in the live talk, Ian will discuss a little bit more about some of those challenges. But the idea was that, there was, physics background knowledge that was covered in schools with guest speakers and lessons, and as well as some math and programming that was covered within their other courses at school. And then the idea as part of this study is to bring students to the university to do activities with laser top interferometers, do lab tours, as well as doing a guided activity using Python to find and analyze black hole merger signals in LIGO data. And it's very accessible, it's guided, and the students are all able to successfully complete the activity. So after today, we do have resources on all of these things. We have information about how to run these activities on your own. And I'm going to leave you with these emails. We have, and I can directly provide for you more information about our programs and links to all of these resources.